Really happy to have Desh Raj from Johns Hopkins University, and has done a lot of work in speaker recognition, ASR, and today he's going to talk about speaker diarization.
Right. Hello, everyone. Good afternoon, good morning, or good evening, depending on wherever you are located right now. Thanks, Hao, for inviting me to speak in this seminar series. I attended the first few talks and it looked very good. And this is a great initiative, I think. Anyway, I'll uh, go ahead and share my screen now and get started. All right. I believe you can see my slides. Okay. If you have any questions during the talk, feel free to interrupt me and just ask or you could write it on the chat. I'll try to keep an eye on the chat box, but I may miss it, in which case, how would you please let me know if there are questions in the chat.
Yep, no problem.
All right. Okay, so I'm Desh. I'm a third year PhD student at Johns Hopkins University, where I work mainly with Sanjeev Kudanpur, but also with Paola Garcia, Dan Povey, who's now at Xiaomi, and Shinji Watanabe, who's now at CMU. This talk is about speaker diarization, and in particular, diarization of overlapping speech. I'll talk about some new methods and some ways to ensemble different diarization systems. Here's what this talk will look like. First, I'll give you a brief background about speaker diarization in case you're not familiar with the task and the traditional solutions. And once that is done, I'll go ahead with the methods that we have proposed, including overlap-aware clustering and another paradigm which is separate, which I call separate and diarize. And finally, I'll talk about an approach for ensembling different diarization system outputs. To begin with, what exactly is speaker diarization? It is the task defined as who spoke when. So in this case, you are given a recording which may contain multiple speakers, and you do not usually know how many speakers the recording has. And there may be overlaps and such present in the recording. The recording itself may be arbitrarily long. Usually we look at anywhere between a few minutes to a few hours of audio, but it could also be up to a day or 2 days, depending on how your recording is recorded. And the desired output of your system are homogeneous speaker segments. So for example, you have to divide this into segments and say which segment belong to which speaker. So for example, in this case, the segments marked purple belong to the same speaker, and so on. An important thing to note here is that these segments are relative. So the segment labels are relative, they're not absolute. Which means that you do not have information about the absolute identities of the speaker, and you only know, okay, these segments belong to the same speaker, but you do not know, for example, these segments belong to which speaker in the whole universe of speakers. So that's the difference between this and something maybe like speaker tracking or so on. Some applications of diarization include, like, the most usual would be like transcribing meetings, or people who study language acquisition often use the output of diarization systems to perform their studies. For example, you may have recordings from a microphone which is located near an infant or a child, and which records the infant during the whole day. And then you would want to get segments of the audio which just correspond to the speech for that child, and also for people who are around that child. So for instance, the child's parents or other caregivers and so on. You could also imagine any kind of tasks like collaborative learning or studying human interactions, which would require the output of such a system. So there's several downstream tasks which require diarization as a pre-processing step. What makes diarization difficult? I mentioned this briefly earlier. There are a few key difficulties. The most important ones are that the recordings may have a lot of silences or background noise. The number of speakers is usually not known in advance. And also overlapping speech, which is the key point of this talk, may be present in the audio. And this is a particular problem in diarization. Of course, this also makes things like ASR very difficult for systems with the systems that we have now. But in this talk, I'll focus on overlapping speech and how to handle them in diarization systems. To give you an example, I'll just play an example recording from the Chime 6 challenge, which was organized last year. And the best system in this challenge got a DER, which is diarization error rate of more than 30%, which is particularly bad. And hopefully this will give you an example.
We have ideas for what to do. So, you put potatoes in already? Oh, no, whatever potatoes.
So that was an example recording from Array microphone recorded in a kitchen, and there were several speakers speaking, often over each other, because that's what people do. And they're also working, cooking in the background, so there was a lot of noise from the utensils and so on. So all these problems make diarization in these settings particularly difficult. A traditional solution to diarization is to treat it as a clustering problem. So the idea is that you divide the audio into very small segments and obtain representations for each of the segments and perform clustering on top of the representations that you have obtained. So here is an overview of such a clustering-based diarization system. It consists of 4 major parts. The first is usually a speech activity detection component, which takes the whole recording and removes the parts which correspond to no speech. So it just retains the parts which do have speech in it. You could use several different kinds of methods for this, either energy-based systems or GMMs, hybrid models, or these days end-to-end speech activity detectors are quite popular. The next step, once you have obtained these speech segments, is to divide them into very small subsegments and extract embeddings for each of these subsegments. So these embeddings may be anything, something like I vectors, X vectors, D vectors, and so on. And these are usually trained with a speaker recognition, speaker classification objective. And the idea is that if you train these models with a speaker recognition objective, then the embedding extractor would be trained to obtain speaker information from these small subsegments, which is actually what we need if we want to perform clustering and we want the clusters to denote speaker identities. Once we do have the embeddings, we can perform pairwise scoring using either cosine scoring, PLDA scoring. There's a lot of options, and obtain an affinity matrix, which is then fed into a clustering algorithm. For clustering, again, we may use agglomerative hierarchical clustering, spectral clustering. And lately, a popular approach is something called VBX, which is a method from BUT, and it performs quite well. This may optionally be followed by resegmentation, where you perform more fine-grained division of the segments. So this is a whole overview of this clustering-based diarization pipeline. Of course, how well does it do it? Well, it doesn't do very bad, but it has been found recently. So there was this series of challenges called Die Hard, which refers to diarization, hard diarization problems, where the recordings are obtained from several domains. And such a clustering-based diarization system was found to obtain around 37% DER in Die Hard 1 and 27% in Die Hard 2. And DER here is computed by taking the total duration which is wrongly attributed. So by wrongly attributed, it could either be the case that you attribute a speech segment as non-speech, or you attribute a non-speech segment as speech, or you assign a speaker segment to a different speaker. So all of those cases are said to be wrongly attributed. And you take the ratio with the whole total speaking time. That's called DER. So this is quite high. This is not something which is usable for downstream tasks which we may want. And one of the key problems that even the teams which won those challenges recognized was that a lot of these errors came from overlapping speech. So the JHU team, which won the challenge in 2018, recognized that 8% of the absolute error was from overlapping speech. And for the BUT team, more than 50% of their relative DER came from overlap speech. So to solve this problem, to get better at diarization, one of the key things that we have to solve is to do well on this overlapping speech. And the problem is that this clustering paradigm is inherently assuming that the segments are single speaker segments, because when we cluster them, we perform hard clustering, which assigns a single segment to a single speaker. And so there's an inherent assumption of this being a single speaker diarization problem. And we propose one approach to solving this problem in our a recent paper called Multi-Class Spectral Clustering with Overlaps for Speaker Diarization. This was published at SLT 21 this year. And this is work with Zili Huang and my advisor Sanjeev Kudanpur. So as you may remember from the overview diagram that I showed earlier, we had this clustering algorithm here, which assigned each segment to a single speaker. We keep all the other components the same and just replace the clustering algorithm with an overlap-aware spectral clustering algorithm, which takes as input the affinity matrix and also the output of an overlap detector, which is externally trained. And it takes both of those as input and performs overlap-aware diarization. So as you can see, it assigns segments to multiple speakers depending on the decision of the overlap detector. Let's look at this in a little more detail. So how spectral clustering usually works is that you first estimate the number of speakers using some way, usually an eigenvalue-based approach, by observing the affinity matrix. And once you've done that, you perform k-means clustering on the first k eigenvectors of the Laplacian of this affinity matrix. So this is a traditional approach to perform spectral clustering, and this is called the Yang-Jordan-Weiss algorithm, and this was first published in 2001. And this has been used successfully in speaker diarization for since like the last 10 years or so. However, the problem with this approach is that it cannot assign multiple speakers to segments, since we are actually doing k-means clustering, which is a hard clustering. So you could imagine that to change this and to perform soft clustering, you could use something like fuzzy clustering or soft k-means clustering or any of those things. Alternatively, we used a formulation from a 2003 paper, which provides a new paradigm for spectral clustering. What it does is that, let's look at this problem in a graphical approach. What we have is, we have an X vector corresponding to each segment. And this X vector is obtained, as I mentioned earlier, from an embedding extractor, which obtains speaker information from the segments. So suppose we represent each X vector as a graph, as a node in a graph. So each segment now corresponds to a node in a graph. The distance between any two nodes can then be computed by computing just a cosine similarity between their corresponding X vectors. So if the cosine similarity is high, that means these nodes will be closer together. So it's like an inversely proportional relationship. Then if you look at this graph, for example, suppose you have 7 segments in your audio, 4 of which belong to speaker A and 3 of which belong to speaker B. What we want is that for the nodes corresponding to speaker A, the similarity between them should be high. And for nodes which are across two speakers, so for the edges between nodes from 2 different speakers, the edge weights, the similarity should be low. So this means that the edge weights within a group, in this case, a group means the nodes belonging to a speaker. The edge weights within them should be high, and the edge weights across the groups should be low. Mathematically, this can be represented using this kind of an objective. I won't go into the detail here, but the essential idea is that we are trying to maximize the ratio of the edge weights within the groups to the edge weights across the groups. And the solution to this optimization problem, again here, A is the affinity matrix that we obtained earlier, and D is just a diagonal matrix, which denotes the degree of the nodes. This is, again, not important. The important thing here is that the solution to this objective, which is X, is the final cluster assignment matrix. So it consists of rows. The number of rows is equal to the number of nodes in this graph, which is equal to the number of segments. And the number of columns is equal to the number of speakers that we estimated using any heuristic, as I mentioned earlier. So this cluster assignment matrix is what we want to obtain by solving this optimization problem. And in this case, it is a discrete assignment matrix. So all these cells either have 0 or 1. So for example, in this first row, the first value is 1, which means that this segment belongs to the speaker 0. So does this segment, but then again, the segment 3 belongs to speaker 2, and so on. So any cell tells you if it's 0, that means that that speaker is not active in that segment. So it's essentially a speaker activity matrix across segments. The problem here is that optimizing this objective is NP hard. So we cannot solve this directly, unfortunately. But what we can do is that we can remove the discrete constraints, which actually make this problem NP hard. And then we can solve this optimization problem. So once you have removed these discrete constraints, this problem becomes solvable in polytime, and it has a set of solutions which you can obtain by taking the eigen decomposition of D inverse A. Again, these are details which are not important, but the important thing is to realize that we have to remove these constraints and make it solvable and obtain a set of solutions. So this is called the relaxed optimization step. And once you have relaxed and solved this optimization problem, we then put it back into a discrete formulation, because remember, what we want is actually a discrete matrix, not this continuous matrix, because we want to actually say which segment belongs to which speaker, and not just have a probability of if that's how likely that speaker is to be active in that segment. So how we do this transformation from this continuous matrix to the discrete matrix is simply by a 2-step process, which involves a non-maximal suppression step and singular value decomposition. So we just keep iterating between these 2 steps until we converge to a solution. I again won't go into the mathematical details. It's all in the paper if you're interested. So that was the key idea of how we changed the k-means clustering into a new formulation of spectral clustering. But I haven't yet mentioned how we make it overlap aware. And we do this by taking the output of the overlap detector and using it to assign some segments to more than one speaker. So for example, suppose we have an overlap detector which may be trained externally or may be given to you from, suppose you obtained it from somewhere. So you know which segments contain overlap. And so you know which segments should be assigned to more than one speaker. And how you apply this into your algorithm is that for those segments which contain more than one speaker, we assign it to more than the top 2 speaker instead of the top 1 speaker when you're performing the non-maximal suppression step. So suppose this segment here contained more than one speaker, instead of just assigning it to the top 1 speaker, we now assign it to the top 2 speakers. And now the output here would correspond to 2 speakers being active in this segment. And this simple modification makes it possible to perform overlap-aware spectral clustering through this approach. Again, we also propose this hybrid HMM DNN overlap detector, which is not very new, but the simple idea is that you have HMM states which correspond to silence, single speaker, or overlapping speakers. And the outputs, the emission probabilities of this HMM are modeled by a neural network which is trained to predict any one of these classes. You could also use a simple end-to-end trained overlap detector in this case. Uh, so that was about the approach of overlap-aware spectral clustering. Let's look at how well it does in practice. These are results on the AMI data set, which contains four speaker meetings. And we use the mixed headset setting in this case. As you can see, the single speaker clustering based systems give about 26-27% diarization error. We reduced it by 2 or 3%, which is about 12% relative improvement over the spectral clustering baseline using our approach. Of course, with a better overlap detector, this would be improved even further. So the performance is directly dependent on the performance of your overlap detector. But as you can see, we are essentially getting an 12% relative improvement without doing any kind of additional training. The only additional training involved here is the training of the overlap detector. This also compares well with other overlap-aware diarization methods which have been proposed recently, while also giving some additional benefits. So for example, in the VB-based overlap assignment, which was proposed in this paper from ICASP 2020, requires some initialization step using some other diarization systems. So I believe they use agglomerative clustering to initialize their method. But our method does not require any initialization. It performs the overlap assignment during the clustering process itself. Some other methods which are based on supervised training schemes require you to have matching training data. So you need to have synthetic overlapping speech to train these systems. Even methods like EAND, which are quite popular and do quite well these days, require a lot of matched overlapping training data, but we do not really require that. The only training data you may require is to train the overlap detector, which is not as difficult as training the whole diarization system. If you look at a breakdown of the metrics, again, I mentioned earlier that DER comprises misspeech, false alarm, and speaker confusion. So we as expected, we get a lot of improvement on the misspeech part because we are not missing out on speech. So earlier, even if there were two speakers speaking, we would just say there's one speaker, but now we recover all those speakers. Of course, there is an increase in the speaker confusion because we are doing worse on assigning the overlapping segments to the correct speakers. This is probably because the X vector extractor is not robust enough. So the X vectors extractor, the embedding extractors, are usually trained on single speaker audio. So they've never really seen overlapping speech or anything of that sort. So while they look fairly separable on non-overlapping segments, on the overlapping segments, they are all over the place. And this is probably why it's harder to distinguish between speaker and to assign them to correct speakers for overlapping segments. So I believe this problem of increasing the speaker confusion can be mitigated if we train a more robust X vector extractor, hopefully on overlapping, which if it sees overlapping speech, it would do well on overlapping segments. It's as simple as that. Again, there's some more results on other data sets. And in this graph, you can see as the overlap ratio increases for methods such as simple clustering-based solutions, the DER keeps increasing because, as expected, on high overlap conditions, it will do really bad. But our method and our PN, the methods which are overlap aware, they do not linearly increase with overlap ratio. The DER stagnates after a while. Of course, it's still high for high overlap regions because from what I mentioned earlier, the X vector extractor is not robust enough. So this approach that I mentioned now is not really the only method that can do overlap aware diarization. Specifically in the last year, there have been like numerous methods which have been proposed to solve this problem. such as the ones that I mentioned, EAND, region proposal networks, overlap aware resegmentation using VB resegmentation, target speaker voice activity detection. This is a popular method that helped the STC team from Russia to win the Chime 6 challenge, and so on. So all these methods work under the assumption that you have some overlapping speech, and you do not directly perform separation on it. You just use the recordings directly and use either an overlap detector, or you have the diarization system trained such that it can directly predict multiple speakers in overlapping segments. A different paradigm to this approach is to simply think that what if we first separate the input speech and then diarize it? So this is something that we did last year during the JSOLT workshop, and we published a paper about this. And so it's part of an integrated pipeline which takes a meeting recording, performs separation, then diarization, and finally is ASR. But the component of this pipeline related to this talk is that we can perform overlap aware diarization by first separating the which is like a simple idea that you could come up with even given 5 minutes of thought. The thing to watch out for here is that we use continuous speech separation, which performs separation in small windows. So the windows could be between 2 to 8 seconds. And in those small windows, we assume that there are at most 2 or 3 speakers active at a time. And once you have separated in that window, we perform this separation task across the whole recording and stitch the output of the small windows. So if you assumed, for example, that there are at most 2 speakers active in the window, after the separation, you would get 2 audio streams. But of course, it may happen that a speaker which was separated into the top audio stream at one window went into the bottom audio stream in the next window, because the windows themselves are independent of each other. There's nothing to say that a speaker in one window should be in the same stream at all time. So the task again then is to cluster across the streams. But of course, now since if we assume that our separation method is perfect, we can assume that the streams themselves are clean and single speaker, and the clustering then can be performed using just any traditional single speaker clustering methods, and they would still give you overlapping outputs, because some speaker would be active at the same time in both the streams. We use 2 different continuous speech separation methods. From one of them is called mask-based MVDR, the other is called sequential neural beamforming. I've mentioned the papers here. I'm not very familiar with these separation approaches, but the thing to notice here is that they perform much better than single speaker clustering baselines. So for example, a spectral clustering baseline would give you a very high diarization error rate, especially when the overlap ratio is quite high, for example, 40%. But when you perform separation at the outset and then use the same spectral clustering to perform diarization, you get a huge benefit, huge decrease in DER from about 28% down to 15% or so. So almost like a 50% reduction in DER. And this is seen across different overlap ratios. So it's a good technique, and it also works well in practice. So the recently held Vox SRC challenge had a track for diarization, and the team from I was not involved in this at all, but I was just interested that the team from Microsoft, which included a lot of people who I've worked with during JSOLT, they used this CSS plus spectral clustering approach for this task, and they won this challenge. So it works quite well in practice. So in the last half an hour, I've talked about a variety of overlap aware diarization systems. That this could include the clustering-based systems, but with added overlap capabilities, and also this separate then diarize approach. Obviously, there are a lot of different machine learning-based systems which can perform overlap-aware diarization, and it is generally known that an ensemble of systems often gives additional advantages. For example, if you look at ASR, Rover has been a popular combination method which can combine the outputs of diarization of ASR systems and has been around for the last 20 years or so. Unfortunately, it is not very easy to combine diarization systems. Some of the problems are that the different system outputs can estimate different number of speakers because you're not given information about the actual number of speakers. You can estimate it wrongly, and so different outputs may have different number of speaker estimates. The system outputs are usually in different label spaces. This again goes back to what I mentioned earlier regarding absolute versus relative speaker label identities. What this means is that suppose you have two different system outputs, A and B. A could assign speaker labels A1, A2, A3, and B could assign B1, B2, B3. And you don't know the direct correspondence between the A's and the B's. So that is something that you have to figure out if you want to perform that combination. And finally, there may not even be agreement on whether region contains overlap. So if there may be a system which predicts that some segment contain overlap, but the other systems may not agree with that. So you have to think about how to solve all these problems when you're thinking about combining the system outputs. We proposed a paper method called overlap, which performs a map and vote technique to perform this combination. There are two stages in this approach. The first is a label mapping stage, which maps all the systems into a common label space. So what it does, it takes the different label spaces and it maps them into a common space where all the systems have the same speaker label identities. And then it performs a label voting, which is a weighted majority voting, and it takes into account speaker counts in all the regions. I'll go into the details here, but the key is this mapping plus voting paradigm. Before we go into the overlap, I'll mention this paper Dover, which was a precursor to Doverlap, and which was proposed in ASRE 2019. So Doverlap was inspired and it extends Dover. So what Dover does, a key assumption that Dover makes is that the input hypotheses do not contain overlapping segments. So it cannot be used to combine systems which are overlap aware. So for example, let's see how it works on these three different systems. For example, suppose you have system outputs from three clustering approaches: agglomerative hierarchical clustering, spectral clustering, and VBX. So all these methods are single speaker, have the single speaker assumption. They do not contain overlapping speech. So again, as I mentioned earlier, they have speaker labels in different spaces. So the hypothesis A has A1, A2, A3, A4, B has B1, B2, B3, and so on. Hypothesis here means diarization system output. That's important. How Dover works is that it takes the hypothesis two at a time and incrementally maps them into the same space using the Hungarian algorithm. So if you think about the DER computation step, to compute the DER between a reference and a hypothesis, this is essentially what is done. You map the reference and the hypothesis using Hungarian algorithm to the common label space and then compute the DER. So it uses the same principle and the same algorithm to map hypothesis B to hypothesis A by constructing this table where each table entry is a score between the corresponding speaker pairs. So for example, this entry here would denote what's the score if you map B1 onto A1. So you would compute that by computing their relative overlap in the whole recording. So you would compute how often they correspond to the same time segments and so on. And So this is a simple application of linear sum assignment problem. Once you have the hypothesis A and B mapped to the same label space, you then take C and map it to the combined label space of A and B. And finally, all of these hypotheses have speaker identities which lie in the same label space. And now it's easy to perform voting because now we know that all of them, the speaker 1 in hypothesis A is the same as speaker 1 in hypothesis B, which is the same as speaker 1 in hypothesis C. So to perform voting, we divide all the hypotheses into regions based on the time boundaries, and then perform voting within each of these regions. For example, in this region, hypothesis A and C predict speaker 1, while hypothesis B predicts speaker 2. So the Dover just predicts speaker 1 in this region. And it does this for all the regions, and which is how we get the final combined solution. So Dover first proposed this idea of mapping and voting, which we extend in our paper. However, there are two limitations of Dover. This incremental pairwise assignment may not really give you an optimal mapping. You may want something which is more global and which takes into account all the hypotheses at once. And second, the voting method does not handle overlapping speaker segment. And this is because it assumes that all the hypotheses have exactly one speaker active at any time. To solve both of these problems, we proposed overlap. And the first change we made was in the label mapping algorithm. We changed the incremental mapping to a global mapping. So instead of taking the hypothesis 2 at a time, we consider them all at the same time. An important thing here is to note that the hypothesis can contain overlapping segments. So there's no assumption on the overlap awareness of the hypothesis. So for example, you may have hypothesis from region proposal networks, END, target speaker voice active detection, and so on. What we do is we construct a tensor with as many dimensions as there are the number of hypotheses. And in each dimension denotes the number of speakers in that hypothesis. So for example, in this case, this axis denotes A speakers, this denotes B speakers, and this denotes C speakers. And then you can imagine that any cell in this tensor would then correspond to a tuple, which is formed by taking one speaker from A, one speaker from B, and one speaker from C. So this cell in this tensor corresponds to this tuple. We compute the cost for this tuple by taking the pairwise costs across these three. So these pairwise costs are similar to how we computed the matrix, the table for the Hungarian algorithm, and we just add them up to compute the whole tuple cost. And we keep doing this for all the tuples, and this is how we fill up this global cost tensor. So we have now this global cost tensor, which corresponds to costs between all the tuples of all the hypotheses. Once we have this tensor, we pick the tuple with the lowest cost and assign it a speaker. So we suppose this tuple here had the lowest cost and it corresponded to A1, B2, C4. We pick this and we assign all of them the label 1. So now in A, B, and C, A1, B2, and C4 are replaced with 1. We then pick the tuple with the second lowest cost and assign it 2. And we keep doing this until there are no tuples remaining. And finally, we'll have this mapping from tuples to these new identities, which is what we wanted in the label mapping. And the good part here is that since the tuple costs take into account all the hypotheses at once, we solved the problem of it being a very greedy algorithm where you had to pick pairs at a time. Once we have this mapping, we can again do something very similar to Dover, which is we divide all the hypotheses into regions based on the time segments. But instead of doing a simple majority voting, as Dover does, we first estimate the number of speakers in this region. So for example, hypothesis A and C for this region predict 2 speakers, while hypothesis B predicts just 1 speaker. So we take the weighted mean of that, and we then decide to assign 2 speakers in this region. And we take the top 2 speakers based on votes from all the hypotheses, and we perform the final voting. This is how the overlap differs from Dover in the voting process. And finally, the result of this is that we combined all the three hypotheses and obtained an overlap-aware diarization output. Some results on the AMI dataset again. So as you can see here, when you have overlap-aware diarization system output, so in this case, we have the overlap-aware spectral clustering, a VB-based overlap assignment, and region proposal network, which give about like the DER, as you can see here. Dover doesn't really do very well because, again, it is not overlap aware. It cannot handle overlapping segments, while all these are overlap aware systems. So it does poorly, and it does worse than all of these individual hypotheses. If we just replace the label mapping algorithm in Dover with a global label mapping that we proposed, we immediately obtain quite a bit of an improvement, especially in the speaker confusion, because instead of pairing two at a time, we are now considering all the hypotheses together and performing this kind of global cost assignment. Then when we added the label voting method that I described, we get a DER which is better than the single best system that we began with. So this is immediately a very good result. And even if we look at a breakdown on the 8 speaker meeting data, we can see why we are getting this improvement. The thing is that you can see methods such as the clustering based systems do quite well in terms of misspeech, false alarms, especially if you have a good speech activity detection. But they do not do very well on the speaker confusion errors because of reasons that I mentioned earlier. However, methods which are trained with supervision such as RPNs or TSVAD, they do quite well on the speaker confusion errors, but they do a bit worse in terms of misspeech and false alarms. What overlap does is that it effectively combines the complementary strengths of these systems. So in addition to doing well on misspeech, false alarms, it also does quite well in the speaker confusion error rate as well. So it assigns the speakers quite correctly. So yeah. Again, so that was from the paper, and we used this recently in the Die-Hard 3 challenge. So I mentioned earlier about Die-Hard 1 and 2, which were organized 2 years ago. Die-Hard 3 was concluded this January, and our JHU team, along with Hitachi, we used overlap to combine a VB-based and EN-based systems, and we obtained a second rank in the challenge. The first ranked team from USTC combined clustering based, separation based, and TSVAD based systems using the same method, the overlap, and they obtained rank 1. So the idea is that it's effective at combining hypotheses from a wide variety of systems, and it is very easy to use. So if you want to use it, you can definitely easily use it. There's some new analysis. I won't go into the details here. Maybe I'll just briefly talk about it. The label mapping stage, as I mentioned, you have to compute the tuple cost, and the tensor itself, it may be exponentially sized, especially if you have a large number of hypotheses. So in some recent experiments, I found that if you keep increasing the number of hypotheses, the combination time grows exponentially, and soon in very few hypotheses, you run out of computation time. That is not something we want. So instead, I proposed a new method which modifies the original Hungarian algorithm, which is linear in time. So this is the log linear scale. So it increases in linear time with the number of hypotheses, and it performs almost as well as the exponential time algorithm from the overlap. So this is, the details can be found in this paper. I won't go into them. And finally, a small word, short word on evaluation. In all of this work, one of the things that I found was that to always evaluate speaker diarization, there's this very nice script called mdeval.perl, which is a Perl script. Uh, it needs to be used, and there's like the dscore package available, which is all very good. But suppose you want to do something like you have a Python script and you have reference and hypothesis list of segments, and you quickly want to compute the DER within that within the Python using something. There's not really a easy to use toolkit available to compute this. So I wrote one, and it is 5 times faster than mdeval, and it can be used either from the Python or as a command line tool as well. And it can you can choose to evaluate on either single speaker or overlapping regions or all at once. And I'll soon be adding Jacquard error rate and other metrics to this. So if you do diarization, feel free to check out this tool that is now available on GitHub. Okay, to summarize, diarization is useful but difficult. So it's useful in the sense that a lot of downstream applications require diarized segments, also speaker-specific segments. But it's difficult because a lot of things like overlaps or noises or not knowing the number of speakers makes it quite challenging. The traditional clustering-based systems were good to begin with, but they fall short on handling overlapping speech. However, with some small modifications based on mathematical insights, we can change this and we can perform them in an overlap-aware setting, and we can give them the capability of handling overlaps. The other paradigm, which is separate then diarize, also works quite well. And if you have a good separation module trained, you can essentially work with simple clustering-based systems and get very good results. And finally, ensembles do work, especially in challenges. So you should definitely use the overlap in your submissions. This work was jointly done with several other people, including people from CLSP, my team at during JSOLT, and also my other advisors and collaborators, Dan, Shinji, Paola, and Sanjeev. I would like to thank my whole team from JSOL 2020, where a lot of this work was first formulated, and special thanks to Takuya and Shota for some of the things. Yeah, I think that is pretty much it from my side. Did I stop sharing my screen?
Yes. Well, it depends on if people want to ask questions.
I think, wait.
Well, maybe I can start.
Yeah. Sure.
So maybe if you go back to your first part of the talk, there's this relaxation of one of the optimization problem. Is that just normalized cut?
Yes, it is exactly
Okay.
normalized.
And if I remember correctly, it's equivalent to spectral clustering.
Yeah.
Oh, okay. So it's just an alternative
It is
interpretation.
alternative formulation of the spectral
I see.
clustering.
I see. And so I feel like this is still in the viewpoint of clustering. Have you thought about using factorization methods? I mean, obviously clustering can be seen as factorization methods, but I just feel like if you have overlapping speakers, factorization methods might be more natural to solve this problem.
Yeah, I haven't really thought about using factorization methods in this kind of setting. My one concern is how would you use the output. Suppose you have the output of an overlap detector. So this kind of approach makes it very easy to just incorporate that into the method itself. That if you have a factorized, uh, you have a factorization of the affinity matrix, how would you go about incorporating that? Like it definitely is something that is doable, but it requires some thought, and I haven't thought about that. But that's a good idea.
Yeah. Well, my main point is maybe you can fit this into a more principled or theoretically justified framework. But I think, yeah, it's similar enough to a factorization method. Yeah.
Yeah, that makes sense. Yes.
Hi, Desh. Thanks for a good talk. I was just since we're here on kind of on the first part of the talk, I was wondering. You mentioned that the quite a lot of approaches here rely on the overlap detection, and I was just wondering, can you comment maybe a little bit about how accurate are the current approaches, and whether there is something available within this field that would enable you to measure, for example, the accuracy of overlap detection, and if you can use in some way an oracle effectively for checking the impact of the overlap detection on the final performance. Just more a little bit on that part of the process. Thanks.
Yeah, sure. Thanks for the question. About your question of using oracles to check the impact of what impact the overlap detector itself has on the diarization process. Yes, it can. It is easy to do. I have those results in the paper. I think what it does is if you use an oracle instead of this diarization, you go from like 24 to 21%. So there's immediately like a 3% improvement absolute in DER. So the overlap detector is definitely not good enough. All the overlap detectors which are currently in use are trained using some kind of simulation, because that's the easiest way to obtain very tight training targets. Because to train the problem with training over an overlap detector is that usually in speech, in the data that we have available, there is a huge class imbalance in terms of how many segments and how many frames have overlaps versus how many frames don't. So usually you get something about 10-15% overlapping frames, and they are bad enough that it's hard to train an overlap detector effectively. And usually we get something about 60-70% F1 score. What we try to do is we try to minimize the false alarms, because that would directly increase the DER. Missing some overlap wouldn't increase DER that much, essentially. So there is definitely work to be done in terms of just having better overlap detectors. Um, I guess there are a few ones publicly available. There's one from PioNote which does reasonably well. It's also in Kaldiv, and yeah, I think does that answer your question?
Yeah, thanks a lot. So it's not the major bottleneck here. So it basically goes from 24 to 21, and that's effectively this idealized overlap detector. Okay, thanks.
Yeah. So in this case, I think there are two things which are not very optimal. One's the overlap detector, and then the other is the X vector extractor that I mentioned. They both need improvement.
Yeah, thanks.
Thank you.
Hi, Desh.
Hi.
Hi from Moscow. In fact, I am new to diarization, though this field is quite interesting. And back to what Hao told about more principled approach, I am fond of Bayesian methods. And when you talked first about clustering speakers, the first thought that came to my mind is whether this approach is suitable here and is it successful. For example, use Gaussian mixture models or even with Dirichlet processes to automatically to automatically infer the number of mixtures. And Gaussian mixture models give us soft labels, so it's kind of works or maybe not.
Yeah, that's a very good idea. That's in fact very similar to what the VBX method for diarization is. It's very popular these days from BUT, and it basically does the best the best single speaker clustering you can have. The idea is to have an HMM which denotes speaker changes, and the emissions of those HMMs can be modeled either through your acoustic frames or through X vectors and so on. And how it's Bayesian is, I think they have some kind of a prior on the speakers on some part of the HMM, and they do a variational based inference on that. So if you're interested in Bayesian methods, that is definitely something you should check out. It is a good principled approach, and it does very well in practice.
Okay, thank you. In fact, your slides are full of links to articles. Will they be available?
Yeah, I'll put it up on my website so you can check it out there.
Okay, thank you. Thank you for the talk. It was amazing.
Thanks for joining.
Hi, Desh. First of all, thank you for the great talk. I just had another question off the back of Anton's question on overlap detection. I guess on the other end of the spectrum from the oracle, could you go back to your slide with the picture of moving from discrete to continuous? I mean, that's fine. Yeah, that's perfect. Did you have a chance to look at the overlap detection performance kind of the model itself? Like maybe with something really simple like a threshold to see how.
Yeah, I did. So one of my I believe that the continuous matrix that we obtain here would be good enough that if you thresholded it at some point, it would be able to tell you that if the probabilities of the two speakers are high enough, then it's probably an overlapping segment, and then you should assign the top two speakers in this segment. But unfortunately, it doesn't do very well. You get a lot of false alarms, and there's no real threshold that you could set to make that work. Of course, again, I think one of the reasons for that is that the X vectors are not trained on this kind of overlapping speech, but there could be other reasons.
Okay, yeah, interesting. I just thought it'd be nice to see kind of.
Yeah, that I hope that will work, because then it wouldn't need an externally trained overlap detector. But unfortunately, for now, we have to keep that overlap detector.
Okay.
Thanks for the question.
Thank you.
Hi there, Mireia here from BUT. Thanks for very interesting talk. I have two questions which are related to the two things that you are mentioning that are somehow the bottleneck right now. So with the first one, you keep mentioning that the X-vector extractor is not trained to be aware of the overlap speed. So I was just wondering whether you are working on this direction and you are trying to reformulate in anyhow the X-vector extractor so that you will also work with this kind of speeds.
I am not, unfortunately. These days I have been working more on multi-speaker ASR, so I have not had much time to devote to this, but I had some ideas initially, and most of it involves some kind of training where you have to again create simulated utterances of speaker mixtures and then train it to predict both of the speakers instead of just one. But of course, that is a very naive idea, and I'm sure you could come up with a much better idea if you put it.
We started also moving towards that direction, so I was just curious whether you had some other feedback.
Yeah, because I also observed in the VB based overlap-aware resegmentation thing that we tried for diehard and also earlier for chime, a lot of the speaker confusion increased in the overlapping regions. So since this was mirrored in both that method and also this overlap-aware spectral clustering method. My immediate thought was it has something to do with the X-vector extractor. So it would be great if you guys could come up with a method to do that.
We'll try at least. Thanks.
Thanks.
And the other question was maybe more, not that technical, but what is your opinion on the overlap labels themselves? So there have been also some earlier questions on how good is when you use the Oracle overlap assignments and you analyze systems like that. I was just wondering whether you actually have analyzed differently the output of the system, because labeling the overlaps is very hard. So do you think that your system already outperforms the Oracle labels in some cases, that it detects overlap better than the human annotations themselves?
I haven't performed that kind of qualitative analysis of that versus the annotation, but I would believe at this stage it wouldn't be, it would definitely not be better than human annotators, even in overlapping regions. Yeah. Maybe in Chime, I'm not sure. In Chime, in very noisy settings like Chime, it would probably be even very difficult for even annotators to accurately tell when there are two speakers speaking. But in something like the telephone conversation or even AMI meeting settings, I think it would be, annotators could do a reasonable job of that. I'm not sure. I'm just saying off the top of my head.
Okay, thanks. Yes, curious about it, because we have seen in a lot of cases that maybe, I mean, it's impossible to get this frame by frame precision by annotators, and sometimes they would be like labeling wider ranges of over, like all this is overlap when it actually was not, and the system instead is able to find these gaps in which there's only single speaker or not. So just curious on whether you had some other analysis. But...
Oh yeah, of course, frame by frame, that would be very hard for human annotators. I think if you can get transcripts from the annotators, it would be much better to do a forced alignments and use that for getting targets or something.
Thanks a lot.
Yeah, thank you.
I was about to ask, how do you make the system sort of extract speaker vectors for multiple speakers, but since somebody else is already doing this, I might just throw this random idea to you. Since I'm not doing this, you might want to train an X vector model so that if there are multiple speakers, you just have multiple vectors being additive, things like that. And so once you have that, you pass the model to get and hopefully the model can do a good job at estimating the additive vectors, and then you do factorization afterwards, then you can separate out everything. Well, that's the very ideal case, if you do just simple data augmentation, then you can train that model easily, I suppose.
Yeah, that makes sense. It's actually surprising that I haven't seen anything done like that before.
Yeah.
But yeah, hopefully we will from Mireya soon.
All right, if there are no more questions, I think we can wrap up. Thanks so much, Desh, for your talk. And right, and then in the next meeting, we will have Chang, if I pronounced your name correctly, to talk about prosody, right? And so, yeah, so looking forward to that. And thank you everybody for attending the meeting. I'll see you in 2 weeks.